Welcome to Spring LIB.
Hello everyone, today we're doing chapter 18, problem 22. And this problem asks us to draw the product's form when we treat each of these compounds with nitric acid and sulfuric acid. So each of these are being reacted with HNO3 and H2SO4. And what we know about this type of reaction is that it's going to be an electrophilic aromatic substitution reaction in which our nitric acid is going to become our electrophile in the form of NO3 plus, and then our nucleophile is going to be the pi bonds in our benzene ring. But now we have multiple substituents on each of these benzene rings. So we have di-substituted benzene rings in A to D. So we're gonna need to ask ourselves, well, are these groups ortho, meta, or para directing? And when you gotta remember that when we're talking about multi-substituted benzene rings, your substituents, if they have an additive effect in terms of their direction, then you would have a clear place or a clear carbon in which your NO3 group is going to be placed. However, if there's some sort of opposing directing effect, then whichever one is a stronger director is going to outcompete and cause the addition of your NO3 to your benzene ring. So what you have here is, and actually this was going to be an NO2, not NO3 electrophile. So with the NO2 electrophile, we know that we need to identify the directing ability of each of these substituents for each of these benzene rings. So actually, let me draw these in separate colors. So for example, let's start with this methoxy group on the top. So we know that oxygen, using its lone pair electrons, can go through some sort of resonance structure that puts a carb anion within the ring of the benzene. So therefore, you're increasing the electron density within the benzene ring. So we can say it's an electron donating group. So what we know about electron donating substituents is that they are ortho and para directing. So we have two ortho positions. I'm drawing them in blue. And we have one para position, which is this bond here, but that's already occupied by another substituent. So there's only two ortho positions that are available for attack on our electrophile. Now what we have here is a ester, essentially. So we have a carbon double bonded to an oxygen, single bonded to an oxygen, then a carbon. So we have an ester group. So what we know about those two oxygen atoms is that they can actually withdraw because of the electronegative characteristic of oxygen more so than carbon. Oxygen can inductively withdraw electron density out of the benzene ring, therefore deactivating it. So what we know about electron withdrawing groups is that they are meta-directing. So in terms of this substituent, the meta position for this ester is going to be these two groups here. These are meta to this ester here, however, they're ortho to the methoxy up here. So in essence, what we have is that we have two substituents, and both of them are directing their effect on these two carbons. So what we know is that if you react A with HNO3 and H2SO4, is that we are going to get a product that you add the nitrogen dioxide on one of these carbons, and because of the internal plane of symmetry, it doesn't matter which carbon you add it to because they're both equivalent, so it's arbitrarily added to one side. So now what about B? So let's B, once again, we have two substituents. We have this methoxy, and then we have this bromine. So let's start with methoxy. So once again, methoxy is electron donating. So we know electron donating groups donate at the ortho and para position. So we have one ortho position open, the other one is occupied with a bromine, and we have one para position also open. However, bromine is an electron withdrawing group, and because it's a halide, it actually opposes the effect of ortho and para direction. So if I were to draw out this opposing effect, we would have ortho and para opposition of substituents being attached to these carbons. Because of that, the characteristic of it being a halide, and because it is more electronegative than carbon, it really deactivates the ring here. So because we have some sort of opposing effect, they don't overlap. We have bromine's ortho position is here and the para position over here, while the ortho position for the methoxy is here and the para position is over here. We obviously would have 4 possible spots which our NO2 can be attached on. However, because there's no overlapping on a single carbon or 2 carbons, so like in problem A, we need to look at which one of these are stronger directors. So we know that if you look at the table that's provided in our textbook, because of the resonance structure that can be formed with this oxygen, this methoxy group is a stronger director than this bromine, which only what it does is just is inductively pull away electron density out of the benzene ring. So because of the resonance structure that can be formed with this oxygen, we know that the methoxy is a stronger director for ortho and para. Therefore, it outcompetes the ortho para direction of bromine, one of the halides. So therefore, that we would get addition of NO2 at the ortho and para position in blue, which are respective to the methoxy group, and not in bromine, because we have a stronger direction by the methoxy group more so than bromine. Therefore, the product will be due to the direction of the methoxy only. So what you will have is a mixture of 2 products, one having ortho substituted, and the second one being para substituted. Now, what about problem C? So C, we have a methyl group and a nitro group. And what we know is that nitro is electron withdrawing group, just like this ester group here. And because of that, we know that nitro is going to be meta-directing. So we have 2 meta positions for the nitro. And now what we know about this carbon is that because carbon and these hydrogens on this carbon, the CH3, they all have electron density, they can share this electron cloud to the benzene ring, making the benzene ring more electron rich. Therefore, it is electron donating. What we know about electron donating groups is that they direct ortho and para. So we have one ortho position that's available, which is overlapped by the meta position of the nitro. And then we also have that para position that's also overlapping the meta position of the nitro. So we have 2 overlapping directions from the 2 substituents, so we'll have 2 possible products. One of them is with the nitro group attached to the meta position in the respectives of the nitro and ortho position respective of the methyl group. Plus, we would get another product in which it would be the addition on the para position in respects to the methyl and the meta position in respects to the nitro group down here. Now, what about the last problem? D. So D, we have a chlorine and bromine. These are both halides. I mean, we know that halides, they direct ortho and para, just like the bromine over here. So, for example, in the bromine, we have a direction ortho and para. Chlorine, again, ortho and para. However, this is a meta-substituted benzene group. So these 2 groups have 1 carbon space in between them. So what we know is that because of steric bulk and the hindrance, no substitution will occur at this carbon. It's between these 2 groups. No substitution will occur between these 2 carbons. The only possible substitutions will be this carbon and this carbon that has the overlapping direction of both of these substituents, the ortho for the chlorine and the para for the bromine at this carbon, and the para for chlorine ortho for the bromine at this carbon. So here we once again get two products, but if you're thinking you will get three, that's not possible because of that bulk and the hindrance that's being caused in this carbon between these two substituents here. Nothing can really attach at that carbon position. But what we can have is one substituent being added at the ortho pair position at this carbon, and we can have another product being at the para ortho position at this bottom carbon position down here.